Okay, so I'm going to do two videos for section 8.3 and kind of divide it up with how I did for class. So one video is going to focus on Gaussian elimination, and then the other video will focus on Gauss-Jordan elimination. So this is 8.3, systems of linear equations in matrices. So let's first kind of go through some vocabulary, talk about what a matrix is, and then we'll actually get into using matrices to help us solve linear systems. Okay, so a matrix is a rectangular array of numbers written with brackets. Each number, a sub ij in the matrix, is called an entry or an element of the matrix. And the first subscript I is the row index, so it refers to what row an element belongs to. And then the second subscript j is the column index and refers to which column an element belongs to. For example, the element a sub 3, 5 would be row 3, column 5, the element that's in row 3, column 5. Okay, so the matrix contains m number of rows and n columns and can be said to be of order m by n. So basically m by n is the dimensions of the matrix, the number of rows by the number of columns. Oops, that's not how you spell columns. Okay, so if the number of rows is equal to the number of columns, then you'll have a square matrix. And in a square matrix, the main diagonal entries are a sub 1, 1, a sub 2, 2, a sub 3, 3, and so on. So for example, a 3 by 3 square matrix would be a sub 1, 1, a sub 1, 2, a sub 1, 3. Then we'd have a sub 2, 1, a sub 2, 2, a sub 2, 3, a sub 3, 1, a sub 3, 2, a sub 3, 3. Where you can see that the diagonal here has those elements, a sub 1, 1, a sub 2, 2, a sub 3, 3. Okay, and then this is a matrix with an order 3 by 3. 3 rows, 3 columns. Okay, so looking at this example, we want to determine the order of each of these matrices. This first one, 2 rows, 2 columns, so it's a 2 by 2. Okay, and the matrix in B, we have 4 rows and 1 column, so it's a 4 by 1. A column matrix is exactly what it sounds, a matrix with only 1 column. So there can be m number of rows, but there will always be 1 column. So an example could be a matrix with elements 1, 2, 3. A row matrix, also exactly the way it sounds, is a matrix that has only 1 row. So it'll be 1 by n number of columns. An example could be elements 1, 2, 3 again, but in a row. Now we've already studied vectors. We're not going to go back to vectors, but now that we are introducing matrices, I did want to show you guys matrix notation for a vector in Rn. Okay, remember how two-dimensional space we referred to as R2, one dimension would be R1, 3 dimensions would be R3, 4 dimensions R4, and so on. So that's what I mean by for a vector in Rn. Okay, so a row vector okay, with matrix notation would be a row matrix, where each element represents a component of the vector. So I don't know, I'll call the components v sub 1, v sub 2, and so on to v sub n. And then more common are column vectors. Okay, which can be written as a column matrix, where we'd have elements v sub 1, v sub 2, to v sub n. So you guys are more familiar with, remember, component form for a vector. So if I give you the vector 1, 2, 1 would be the horizontal component and 2 would be the vertical component, meaning that the vector in two-dimensional space would terminate, if it were in standard form, meaning its initial point started at the origin, it would terminate at the point 1, 2. So another way that I could write this vector in matrix notation would be as 1, 2 as a column vector, or 1, 2 as a row vector. Okay. So we can represent systems of linear equations with matrices as augmented matrices or using matrix equations. So in this class, we are going to be using augmented matrices. Matrix equations, we will not be studying in this class, but you would maybe, if you continue on with your mathematics, you would probably see in linear algebra. So a coefficient matrix is kind of exactly how it sounds. So if I had a system, I don't know, x plus y plus z equals to 7, 2x minus y plus 3z equals to 9, x plus 4y minus z equals to 2. Okay, so if I have this system, I can take all the coefficients for x, y, and z and put them into a matrix. Okay, where the first element would be this coefficient. The second element in the first row would be 1, 1. So I'm just writing down all the coefficients for x, y, and z. So the first column corresponds to all the coefficients of x, and then the second column corresponds to all the coefficients of y, and the third column corresponds to all the coefficients of z. And then row 1 is equation 1, row 2 is equation 2, row 3 is equation 3. Now, if we were going to be solving linear systems using matrix equations, we would use coefficient matrices, but that's not a method that we're going to be looking at in this class. We are going to be using augmented matrices. So resembles a coefficient matrix, but with an additional vertical line and column of numbers. So if I take this same system, I can write this as an augmented matrix by, on the left of this matrix, I'm going to have basically the coefficient matrix. And then I'm going to put a vertical line. You can also use a dashed line. I think your text uses just a vertical line, so I'm going to put a vertical line. And now I'm going to add what each equation is equal to, the constant that each equation is equal to. Okay, so this is our augmented matrix, and this is what we're going to be using to help us solve linear systems. So row operations are used to solve a system of linear equations when the system is written as an augmented matrix. These row operations just come from, or the same thing as same operations that we were using when we were solving linear systems using elimination. So you can interchange, and this is the notation we're going to be using. So the first one, we can interchange two rows, and that's basically thinking about if you have a system, you're allowed to switch the order of the equations, right? Equation 1 doesn't have to stay equation 1. It can be flip-flopped to be equation 2 or equation 3. So we're allowed to interchange the rows. And then the second row operation, I have my numbering off here. Okay, the second row operation is you can multiply a row by a non-zero constant. And if we think about elimination method, we often would have to use the multiplication property of equality to multiply an equation on each side by some constant. That constant can be positive or negative. And then we can also add a multiple of a row to another row. That's basically the elimination part of elimination method, right? When we add the two equations together in order to eliminate one variable, that's what this last row operation is. And it's important to remember that C can be negative, C can be positive, or C can be negative. Okay, so we can solve systems of linear equations using augmented matrices with Gaussian elimination or Gauss-Jordan elimination. So this first video is going to focus on Gaussian elimination. And the goal of Gaussian elimination is to get our augmented matrix into row echelon form, which can be abbreviated as REF. Okay, so a matrix is in row echelon form if it has all three of the following properties. Any rows consisting entirely of zeros are at the bottom of the matrix. For each row that does not consist entirely of zeros, the first leftmost non-zero entry is 1, called the leading one. And for two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. So I'm going to give you a couple examples of matrices that are in row echelon form. So the first example could be if we had 1, 0, 0, I don't know, like 2, 1, 0, 3, 4, 1, and then, I don't know, 1, 2, 3. Okay, this augmented matrix is in row echelon form because notice we have this diagonal of 1s, and then the bottom half of the matrix is 0. Another example of a matrix in row echelon form could be if we had 1, 0, 0, I don't know, 4, 1, 0, 2, 0, 0, 1, 2, 0. Okay, where this bottom row, oops, is all zeros. Our diagonal is ones, right? We have leading ones. And then the bottom half here, bottom triangle is zeros. So both of these are considered to be in row echelon form. Now reduced row echelon form, abbreviated RREF, if a matrix in row echelon form has the following additional property, then the matrix is in reduced row echelon form. So reduced row echelon form is technically also row echelon form, but not all matrices that are in row echelon form are in reduced row echelon form. So if every column containing a leading one has zeros in every position above and below the leading one. So an example, just staying pink, would be 1, 0, 0, 0, 1, 0, 0, 0, 1, and then, I don't know, 1, 2, 3. So this matrix is in reduced row echelon form, where we have our column of ones just like in row echelon form. And then above and below the diagonal is all zeros. So we're going to be using the row operations that we talked about above to help us change our augmented matrices into row echelon form first. And then the next video will be going all the way to reduced row echelon form, which is just a few more steps. So in doing this, this is referred to as Gaussian elimination with back substitution, when you take an augmented matrix and get it into row echelon form. So we're going to write the system of linear equations as an augmented matrix and use those row operations to rewrite the augmented matrix in REF. And then you write, once you get it into row echelon form, you're going to write the system of linear equations that corresponds to the matrix in row echelon form, and then use the system of linear equations found in step 3 together with back substitution to find the solution to the system. All right, so we have this system, 2 equations, 2 variables. So you guys know already how to use this, solve this using either substitution or elimination, but now we're going to use matrices. So first step, to rewrite in as an augmented matrix. So I write down the coefficients and then what each equation is equal to. Now, for row echelon form, we know that we want this first element to be 1. And I notice that in row 2, the element in column 1 is already 1. So I want to basically flip-flop these 2 rows. So I'm going to interchange row 1 and row 2. When we do this, this is basically just switching the order of the equations in the system. So now I'm going to work my way down. I'm going to use the 1 in row 1 to help me get this element, the first element in row 2, to be 0. So to do that, I'm going to do R2, so row 2, minus 2 times row 1, which is the same thing as row 2 plus negative 2 times row 1. Remember that constant can be negative. And this is going to replace row 2. When we perform these row operations, you have to write down next to the matrix, like I am, what you are doing, what row operation you are doing. Okay, so our new matrix will still have row 1 as 1, 3, 6. Okay, row 2, so this element here will be 2 minus 2 times 1, so times this element. So that will end up being 0. Okay, and then for the next element, so row 2, column 2, that's going to be 1 minus 2 times 3. So 1 minus 6 will give us negative 5. And then negative 8 minus 2 times 6, that will be negative 20. Okay, so we're almost there. To finish getting this matrix into row echelon form, I want this negative 5 to become a positive 1. So I'm going to multiply row 2 by negative 1/5. You think of it as dividing the row by negative 5, or multiplying by negative 1/5, because you're using the multiplication property of equality. Oops, sorry. This is row 2, and we are replacing row 2. So 1, 3, 6 still in row 1, and then 0, 1, 4. So this matrix is now in row echelon form. So if I were to rewrite the matrix that's in row echelon form as a system of equations, I would have x plus y equals to 6 and y equals to 4. So notice when we get to row echelon form, we end up knowing what one of our variables is equal to. So now what we mean by back substitution is I can substitute 4 in for y into the previous equation. So x plus 4 equals to 6, or x equals to 2. Yeah. So our solution to this system is 2, 4. That's not right. 1, 3, 6. Y equals to 4. Oh, I know why. Sorry about that. This should be 3y. Duh. Okay. Sorry. So if we substitute 3 in for y, we'll get x equals to -6. So the solution is actually -6, 4. Sorry. Okay, so we are going to solve this system now of 3 equations, 3 variables, using Gaussian elimination. So first, writing my system as an augmented matrix. Make sure you write the augmented matrix with the correct coefficients, or correct elements. Okay, so first thing I want to do is I want to make this first element 1, and I notice that the first the element in column 1, row 2 is a 1. So I'm going to first switch row 1 and row 2. Oops. Now, it's not very fun to rewrite this matrix over and over again. So when possible, I'm going to kind of do multiple row operations in one step. So now I want to make 2, 0, and I want to make this 3, 0. So I'm going to use row 1 to help me do that. So in order to rewrite row 2, I'll do row 2 minus 2 times row 1. And then to make the 3, 0, I'm going to do row 3 minus 3 times row 1. So row 1 will still look the same. Okay, now row 2, we'll do 2 minus 2 times 1 is 0. 1 minus 2 times -1 will become 3. 8 minus 2 times 1 will become 6. -1 minus 2 times -2 will become 3. Okay, now row 3. 3 minus 3 times 1 is 0. -2 minus 3 times -1 will be 1. -2 minus 3 times 1 will be -5. And then 2 minus 3 times negative 2 will be 8. Okay. So next, I'm working my way down. So my first column's good. The second column, I want this 3 to become a 1. But I noticed that in row 3, we have a 1 in that position, in that second column. So I'm going to flip-flop row 2 with row 3. And now I can use row 2 to help me make 3 a 0. So I'll do row 3 minus 3 times row 2 to replace row 3. Okay, so this will still be 0. This will become 0. 6 minus 3 times negative 5 will be 6 plus 15. Right? Okay, so we get 21, just making sure I'm looking at the right elements. Okay, and then we'll do 3 minus 3 times 8, so negative 21. And then to finish getting this into row echelon form, I want this 21 to become a 1. So I can multiply row 3 by 1 over 21. Okay, so now we're in row echelon form. Oops. Because we have this diagonal of 1s and bottom half is all zeros. So I'm going to write this now back as a system of equations. So x minus y plus z equals to negative 2. Y minus 5z equals to 8. And z equals to negative 1. So now that I know what z is, I can substitute z back into the equation above it in order to solve for y. So we would get y is equal to 13. Did I miss something? Oh no, it's not 13, that's 3. Sorry, that would be positive 5. So 8 minus 5 would be 3. Didn't look right. Okay, and then substituting our values for z and y back into the original equation, we can then solve for x. So that will be x minus 4 equals negative 2, so x equals to 2. So the solution to this system, 3 equations, 3 variables, is 2, 3, negative 1. And we found that solution using Gaussian elimination. Okay, I believe we have, we'll have one more for this video. So first, writing as an augmented matrix. All right, we already have a 1 in row 1, column 1. So that's good. We can use that one to help us get zeros in row 2 and 3, column 1. So let's do, for row 2, let's do row 2 minus 2 times row 1. And same thing for row 3. So row 1 is the same. Then row 2 will become 0. Okay, 1 minus 2 times 1 is negative 1. 1 minus 2 times negative 1 is 3. And that will stay 0. Okay, for row 3, we'll have 0. Then negative 1 minus 2 times 1 is negative 3. 3 minus 2 times negative 1 will be 5. And then negative 1 minus 2 times 0 is just negative 1. I'm going to multiply equation 2 by negative 1. Sorry, row 2 by negative 1. And now I can use row 2 to help make this negative 3 into a 0. So we'll do row 3. Okay. Plus 3 times row 2. Okay, so 5 plus 3 times negative 3 will be negative 4. And negative 1 plus 3 times 0 will just be negative 1. Almost there. So now we can just multiply row 3 by negative 1/4. Okay, so we're in row echelon form. And, ooh, looks yucky. I'm going to write this matrix now as a system. So x plus y minus z equals 0, y minus 3z equals 0, z equals to 1/4. So using back substitution, we'll have y minus 3 times 1/4. So y is equal to positive 3/4. And then solving for x, what is that? X plus 1/2 equals 0. So x equals to negative 1/2. So our solution to this system will be negative 1/2, comma 3/4, comma 1/4. Okay, so the next video will be finishing up this lesson and will be on Gauss-Jordan elimination.